Swayam Prabha. Digital India. Educated India.
In continuation of the vector spaces and decomposition, and we come across Cholesky decompositions and singular value decompositions. Further, we have to discuss eigenvalue decomposition, right. That is most important to understand how we can decompose the matrix. I hope many of you the number system, right, say you take any prime number or composite number, the composite numbers, say for example you take a 12, 12 can be written as 4 into 3 and 4 can be written as 2 into 2 into 3. So, that means how we are writing a 12 can be decomposed into 3 numbers. The same way you take any matrices and we have to decompose it, and then so that we have the factors of the certain universal properties of that matrices may easily generated. So, we have a same technique applying to the matrices, but we have to follow the rules and regulation based on the eigenvalue and eigenvector, and then orthogonal and orthonormalized ideas to generate the matrices can be decomposed into factors to the learned universal properties A equal to V into diagonalization of lambda into V inverse. So, if you have a is a matrix, find eigenvalue eigenvector, that is A minus lambda I equal to 0 and then A minus lambda I into x equal to 0, and you have eigenvectors. Based on the eigenvectors, we have to find out the what V and V inverse, and corresponding diagonals you have to split so that the matrix can be decomposed into what V diagonal A lambda into V inverse. That is the meaning of decomposition of the eigenvalue. Now, keep it in mind this, let us go into the deep of eigenvalue eigenvectors once again, so that we can incorporate it with these ideas in terms of the decomposition. So, we know that what is the meaning of eigenvector. Eigenvector is nothing but you take a matrices A and find the eigenvalue eigenvector, and you take an eigenvector of the square matrix A is a non-zero vector V, such that we have to multiply by A, they change the scale of V, so that AV equal to lambda V. So, here lambda is a eigenvalue and A minus lambda I into x equal to 0 is a eigenvector. So, this way we can write what is eigenvalue and eigenvector. Now, keep it in mind this. Let us go to the next step. If V is eigenvector of A, so is any rescaled vector SV. Moreover, SV still has the same eigenvalues. Thus, the constraint the eigenvector to be the unit length of norm V equal to 1. So, norm V equal to 1 in the sense that root of inner product space of V equal to 1. So, mixing together of norm of the vector and normal matrices ideas together, we form a the corresponding relationship between the norm and eigenvectors. So, the eigenvector to be the unit length means the length is 1. Now, based on this, we already come across that characteristic polynomial, right. So, eigenvalue equation of the matrix A, and we can write AV equal to lambda V and bring the LHS AV minus lambda V equal to 0 and take V as a common. So, A minus lambda, since A is a matrix, therefore, you multiply lambda into I matrix, the identity matrix corresponding to the order of A, and then A minus lambda I into V equal to 0 is the corresponding expression of the polynomial in terms of the eigen value. So, this is called as characteristic polynomial. So, a non-zero solution for V exists, then it must be the case that determinant of A minus lambda I equal to 0, and unpacking the determinant as a function of lambda, we get A minus lambda I, that is, if A is a square matrix of order n, then it has a n values, then we can factorize the polynomial into lambda 1 minus lambda, lambda 2 minus lambda and so on, lambda n minus lambda of n factors, that is, it is factorizable. Then we can write like this, then the lambda 1, lambda 2 and so on, lambda n are the roots, rather it is called as characteristic roots, and it comes from the characteristic polynomial, and based on these characteristic roots, call it as eigenvalues of A. So, this is a fundamental definition of eigenvalues with the help of the matrix A we generated. For example, you take a matrix A of 2, 1, 1, 2. Now, the characteristic polynomial of determinant A minus lambda I is nothing but determinant of simply what determinant of 2, 1, 1, 2 minus lambda into 1, 0, 0, 1 of equal to 0. Then we subtract 2 minus lambda 1, 1 and then 2 minus lambda equal to 0. So, this is what they written here, and apply the determinant. So, 2 minus lambda the whole square minus 1 equal to 0, and expand is 4 plus lambda square minus 4 lambda minus 1 equal to 0. So, lambda square minus 4 lambda plus 3 equal to 0, that is what they simplified, 3 minus 4 lambda plus lambda square equal to 0. Once we have a quadratic equation, it is factorizable. Therefore, we have a factor of what, lambda minus 3 into lambda minus 1 equal to 0, that is lambda equal to 3 and lambda equal to 1 are the roots. So, once you know that the roots, then we can easily find the what, eigenvalues. Once you know the eigenvalues, we have to find the eigenvector, that is, we have what, A minus lambda I into x equal to 0, then what happen? So, you take lambda equal to 1, then you have a matrix 2, 1, 1, 2 minus 1 into 1, 0, 0, 1 of this into x1, x2 equal to 0, 0. Then what happen? So, subtract them, then it becomes 2 minus 1 is 1, 1 minus 0 is 1, 1 minus 0, 1 minus 0 is 1 and 2 minus 1 is 1. So, the equation is very simple, and the equation, both equations are same, that is x1 plus x2 equal to 0. It means x1 equal to minus x2, therefore, infinitely many solution. If we choose x1 equal to 1 and then x1 equal to 1, then x2 equal to minus 1. So, that is the meaning of vector 1 comma minus 1. Similarly, put lambda equal to 3 and then you have a 1 comma 1 is a corresponding eigenvector. So, keep it in mind this, we can determine the eigenvectors with the help of the eigenvalue and using the technique. Now, what are the eigenvalues? Given a matrix A and x is the eigenvector and lambda is the corresponding eigenvalues, if Ax equal to lambda x and A must be a square and determinant of A minus lambda I must be equal to 0. So, if Ax bring to one side Ax minus lambda x equal to 0, rather A minus lambda I into x equal to 0. So, if x equal to 0, it is a trivial solution. If x not equal to 0, we have to find the determinant of A minus lambda I equal to 0. So, that is the meaning of eigenvalue. Our eigenvectors are unique. So, x is an eigenvector, then beta x is also a eigenvectors, and beta lambda is an eigenvalue. Therefore, A into beta x equal to beta into Ax, which is equal to Ax equal to lambda x from the equation 1, or here 1A. So, beta into lambda x you substitute it. So, lambda into beta x will come. So, this way we can determine the eigenvectors, and uniquely we can represent like this. Now, we are going to calculate the eigenvectors or eigenvalue. Expand the determinant of A minus lambda equal to 0 for 2 cross 2 matrices. Now, what you have to do is, you take a determinant of A minus lambda I. Suppose A is equal to A11, A12, A21, A22, then you substitute here, and lambda into I matrix is 1 0 0 1 equal to 0, then A11 minus lambda, A12, A21, A22 minus 1, and you take the determinant equal to 0 and simply cross multiply the diagonal, right, and then opposite diagonal multiply, so that for the 2 cross 2 we can easily determine. Now, what you can see that if you expand it, so lambda square minus lambda into A1 plus A2 plus the determinant of this. So, the general theory we can write for writing the characteristic equation as, so if it is for 2 cross 2, then lambda square minus lambda into main diagonal plus determinant. If you have a 3 cross 3, then lambda cube minus lambda into main diagonal, and then you take say if it is A equal to 3 cross 3, then lambda cube minus lambda into main diagonal, lambda square into main diagonal plus lambda into cofactor of the each elements plus determinant minus determinant of A matrix equal to 0. So, in this way the general procedure we can write for the characteristic equation of any matrices of n cross n matrix. So, once you get it this equation, it seems to be a quadratic equation. If it is a quadratic equation of 2 cross 2 matrix, the simple quadratic equation with 2 solution may be complex. So, minus b, this is b minus b plus or minus root of b square minus 4ac minus 4 into ac divided by 2a. So, this way we can do that, so that the simplified version of lambda is equal to a11 plus a22 plus or minus root of this a11 plus a2 the whole square by 4 into a11 a2 minus a12 to 1. So, this characteristic equation can be what? To solve for x. Now, consider 2 cross 2 matrix 1 2 2 4 according to the previously explained the polynomial of lambda square, and then the coefficient of a11 plus a12 you take it, this is a11 a22, and then a11 this is a11 a22 minus a12 a21 is a determinant. Now, what happened? Lambda square minus a11 is 1 and then a22 is 4 and a11 equal to 1, a22 to 4, a12 is 2, a22 1 is 2. Now, what happened? So, lambda square minus 5 lambda, right, plus 4 minus 4 is 0. Therefore, you bring everything is right hand side of lambda. Therefore, lambda square equal to 5 into lambda. Therefore, either lambda equal to 0 or lambda equal to 5 is what solution to this equation. So, here lambda is called as eigenvalue. Now, we have to determine the corresponding eigenvectors can be computed as lambda equal to 0, then we can write what a minus lambda I into x equal to 0, where lambda equal to 0, 0 into anything is 0 will come, right. Therefore, the matrix is 1, 2, 1, 2, 2, 4 into x, y, and then this is 2 cross 2 and this is 2 rows and 1 column. Therefore, we have a 2 rows and 1 column will reflect. Therefore, x plus 2i and another one is 2x plus 4i equal to 0, 0. For lambda equal to 5, then we have a minus lambda into x equal to 0. Therefore, 1, 2, 2, 4 minus lambda is 5, 5, 0, 0, 5 into x, y equal to 0 implies subtract them minus 4, 2, 2 minus 1 into x, y equal to minus 4x plus 2y and 2x minus y equal to 0, 0. Now, you see there are two equations for lambda equal to 0, then so x plus 2y equal to 0 and then 2x plus 4i equal to 0, solve them and we have what x equal to 2 and y equal to minus 1. See, simply multiply this equation to 2 become 4, right, and then cancel is. So, you have what the two equation get 0. Therefore, trial and error you have to took for x equal to 2 and y equal to minus 1 is one of the solution to the equation. Similarly, the another equation 4x minus 4x plus 2y equal to 0 and 2x minus y equal to 0, simply you have to solve them. So, what happened? You get x equal to 1 and y equal to 2 is a solution to this. So, these two are the eigen values of what lambda equal to 0 and 5 respectively. So, in this way we can calculate how to find out the eigenvalues of the given matrices. Now, physical interpretation is consider a covariance matrix A, where A equal to 1 by n into S into S transpose for some S. So, covariance of this value you have to take it and convert it into matrix and find A minus lambda I equal to 0, where two roots will come. One is lambda 1 and lambda 2 equal to minus plus 0.25, another is 1.75. Now, you have to trace the value to corresponding the grid, so that these are all the values will be generated. So, after that we have to substitute the eigenvector corresponding to expand it, so that we have a eigenvalues will be generated and join these together, we have a ellipse and then we have with the major axis as a larger eigenvalues and minor axis as smaller eigenvalues will be generated. So, this is the physical interpretation. We can bring the solution to the problem. Once you know that physical interpretation of eigenvalue eigenvector and we have a the original variables of A and B and the principal component of this one is generated with the help of this picture, and you check it out whether they are orthogonally one another or not, so that we can check it out orthogonal and orthonormal and corresponding projection. So, these component can be interpreted with the help of the greatest variance in the data. So, the first dot represent the orthogonal direction of a greatest variance in data, and another one is a projection along the principal component that discriminate the data most along with the one axis. Now, the physical interpretation, first principal component is the direction of the greatest variable in the data. Second is the next orthogonal uncorrelated direction of the greatest variability, and so the first remove all the variability along the first component and then find the next direction of the greatest variability and so on. Thus, each eigenvectors provides the direction of data variances in decreasing order of the eigenvalues. So, that is the meaning of physical interpretation along with the eigenvalue and eigenvectors. And also it will be very helpful in multivariate Gaussian, multivariate normal of n of x over mu over the summation, and definition says that it is a exponential of the mean x minus mu whole transpose summation x minus mu and divided by 2 pi whole power p by 2 into some modulus of summation of. So, this exponent is a Mahalanobis distance between the x and mu, and delta is equal to x minus mu whole transpose summation inverse of x minus u. So, this may be discussed in the next topic in the probability and distribution. Further, you can understand these ideas of eigenvalue, eigenvector, how we are incorporated, and the decomposition is how we are incorporated, that we can understand. So, here summation is a covariant matrix, is a positive definite of x transpose summation x is always positive for all x. Next, bivariate Gaussians. So, covariance matrix is summation sigma x square rho into sigma x into sigma y, rho into sigma x, sigma y and sigma y square, where the correlation coefficient is rho equal to covariance of x comma y by root of variance x into variance y. That deeply we will discuss the next topic of probability and distribution, where rho is the value of the correlation lies between -1 to 1, and we also have the probability of distribution x comma y is 1 by 2 pi in sigma x into sigma y standard with respect to standard deviation with respect to x into y, root of 1 minus rho square into exponential of 1 minus minus 1 by 2 into 1 minus rho square of x square by sigma x square plus y square by sigma y square minus 2 rho xy by sigma x sigma y. So, this is the spherical and diagonal full covariance related to what the decomposition of standard deviation, like sigma square 0 0 sigma square, and standard deviation with respect to x with respect to y is a corresponding picture, and using that covariance sigma x square rho into sigma x sigma y and rho into sigma x sigma y by sigma y square is corresponding picture of the spherical as well as diagonal, and full covariance is demonstrated here. And then with the help of the MATLAB, and we can easily picturize the 3-dimensional effect of this curve. Next, we are going to discuss about the Eigen decomposition. Suppose you take a n cross n matrix A has n linearly independent eigenvectors v1, v2 and so on vn with the eigenvalues lambda 1, lambda 2 and so on lambda n. Now, concatenate eigenvectors to form a matrix P and concatenate the eigenvalues to form a vectors lambda equal to lambda 1, lambda 2 and so on lambda n. Now, the eigen decomposition of A is given by A equal to V into diagonal of lambda into V inverse. So, this is the definition we are going to impose into eigen decomposition. So, already you know A and find the eigenvalue and find the eigenvector, and what eigenvalue you get, that is the diagonal of lambda. Based on the eigenvector, you have to find the V and find the V inverse, so that A can be decomposed into these ideas, that is called it as eigen decomposition. Now, eigen or diagonal decomposition, that is nothing but, so you take a set S which have R m cross n, mean m rows and n m column of S. S is a square matrix and it has a m linearly independent eigenvectors and a non-defective matrix, and the theorem exists, the eigen decomposition, that U A U tau U inverse. It means you have to diagonalize the given matrix and find the eigenvalue, and unique eigenvalue or a distinct eigenvalue will come unique for a distinct eigenvalue will come, that you have to represent lambda based on the tau. We have what eigenvectors, and u is eigenvectors so corresponding to the matrices, and then u and u inverse find out, and then it will be diagonalize and decompose. So, that is called as S. Now, we have a matrix diagonalization theorem, and u represent the in terms of the column of the eigenvector of S, and diagonal elements is tau or the eigenvalues of S. Therefore, it main diagonal is only lambda 1, lambda 2 and so on lambda m of the given matrix, and diagonal elements only will come. The above and below diagonal will be 0, and lambda I is greater than or equal to lambda I plus 1, like that you have to consider, because sometimes it may be confused. Therefore, start from the what lambda I greater than or equal to lambda I plus 1 you have to take decreasing ways. Now, we have a diagonal decomposition why and how. So, if you have the eigenvectors and column u is equal to u1, v1, v2 and so on vn represent, then SU be the written as SU equal to S into v1, v2 and so on, and SV1 is lambda v1, lambda 1 v1, S into v2 is lambda 2 into v2 and so on lambda n vn, and then we have v1, v2 and so on vn. Then we have a eigenvalue of the main diagonal lambda 1, lambda 2 and so on lambda n. So, this represent SU. So, SU equal to u tau, tau is u lambda, or u inverse SU equal to tau. Therefore, S equal to u tau u inverse will be proved. So, this way we can decompose of the given matrix, that is called it as Eigen decomposition or diagonal decomposition. This is the how we can return that. That's why what we have eigenvectors corresponding to eigenvalue be generated. Now, we have an example diagonal decomposition. Recall S is equal to 2, 1, 1, 2, and lambda 1 equal to 1, lambda 2 equal to 3, because you take a matrix A or S, then S minus lambda I equal to 0, then determinant of 2, 1, 1, 2 minus lambda into 1, 0, 0, 1 equal to 0, and then 2 minus lambda 1, and then 1, 2 minus lambda of determinant equal to 0, then 2 minus lambda the whole square minus 1 equal to 0. Therefore, 4 minus 4 plus lambda square minus 4 lambda and then minus 1 equal to 0. Therefore, lambda square and then minus 4 lambda minus plus 3 equal to 0 factor, you have lambda 1 equal to 1 and lambda 2 equal to 3, and already we done it, refer it, and then corresponding eigenvector we done it, refer it, and then S minus lambda I into x equal to 0, and we have a x1 set 1 comma minus 1, another set is 1 comma 1. Now, you take a column wise of this element, this is like this and this is like this. So, we have a representation of a matrices like this. So, that is U. Now, you have to find U inverse. U inverse is equal to what 1 by determinant of U into U transpose cofactor. Now, determinant of U is nothing but what 1, 1, minus 1 and 1, expand it 1 plus 1 equal to 2. Therefore, 1 by 2 will come U, therefore, inverse exists, and then change the place 1, 1, 1 and change the sign in opposite direction 1 minus 1 and multiply with 1 by 2, you have a matrix of U inverse equal to 1 by 2 minus 1 by 2, 1 by 2, 1 by 2 will come. Now, you check U inverse, definitely it will come what 1 identity. So, this way we can do that what the identity of the matrix. Now, you can decompose U you know, and then U inverse you know. U tau U inverse is nothing but this matrix U matrix is 1, 1, minus 1, this you have to write, and tau is a main diagonal of the lambda 1, lambda 2, and then U inverse also you know, now it is totally decomposed. So, this is the way we can do for diagonally decomposed. Now, with the help of the diagonally decompose, let us divide U and multiply U inverse by root 2, so that S equal to 1 by root 2, 1 by root 2, minus 1 by root 2, 1 by root 2, 1003 and so on. Therefore, it is called as Q tau Q inverse. So, this can be represented into decompose into the 3 matrices. Based on that, we can write the picture corresponding to the given matrix. Next, we will go to the symmetric matrices. Every real symmetric matrix A can be decomposed into real eigenvectors and eigenvalues. Symmetric matrix means A equal to A transpose. So, that technique apply it so that the matrix is symmetric, and the matrix entry all are real, then it is to be real symmetric matrix. So, this is the real valued eigenvectors, eigenvalues, and A equal to Q tau Q transpose. Here Q is the orthogonal matrix of the eigenvectors of A, and tau is the diagonal matrix of eigenvalues. So, we can think of A as a scaling space by lambda I in the direction of Vi. Therefore, this is the plot of the unit vector, and with the 2 variable x1, x2, we can plot of the vectors in terms of the ellipse. So, this can be generated from eigenvalue eigenvector corresponding to the vectors, how we can project, orthogonally project, and how we can trace the curve. Now, we have a symmetric eigen decomposition. The technique is you take a M cross M symmetric matrix and exists a unique eigenvalue decomposition, check it out, and check it out, Q is orthogonal, right. So, Q inverse equal to Q transpose, you check it out. Columns of Q are normalized eigenvectors, and columns are orthogonal, and everything is real. So, the columns of Q are normalized mean, suppose 1 and 1 is a vector, then 1 by root 2, 1 by root 2 is a normalized eigenvectors. So, this is eigenvector, then this is the normalized eigenvector. So, this way we can do that and check it out, the any 2 vectors, set of vectors, and product them, and then inner product you check it out 0, then it is orthogonal, and the same way you check it out rest of them, then columns are orthogonal or not. If it is orthogonal, then we can proceed, and all the numbers should be the real. Now, based on this, we have a theorem, spectral decomposition theorem. You take any symmetric matrix A and it is positive definite, mean the values are positive, and you take a K cross K matrices, that is X transpose AX. X is a eigenvectors, and you have to normalize A matrix, multiply them. You have a bilinear transformation corresponding to this with lambda is positive. Then we have a eigenvalue EI, and I varies from 1 to K, where K being K eigenvector, and eigenvalue corresponding pairs also generated. So, A can be written as some eigenvalue into eigenvector and eigenvector transpose, multiply them, that is the first one, and lambda 2 into second eigenvalue take it, and corresponding eigenvector and corresponding eigenvector transpose you multiply them, and then linear combination you have to do up to n times or k times of how many eigenvalues come. According to that, you have to write the linear combination of these, and then we can express A can be K cross K, because first one is K cross 1 into 1 cross K is equal to K cross K, like that everything is K cross K will come. Finally, lambda 1, lambda 2 and so on, lambda K are all are scalars, and then if you add them, then we have a matrix of A suffix K cross K, mean order is k, and corresponding we have a linear combination of summation I equal to 1 to k of lambda into Ei transpose equal to P tau P transpose. So, the P is a matrix of Ek elements of tau kk, and corresponding we have a main diagonal elements, that is lambda 1, lambda 2 and so on, lambda k only will come. Then we have a what eigenvalue we got it, and that value is the resultant is diagonalizable, and that is the meaning of Eigen decomposition ideas. So, this is the inference we learn from eigenvalues corresponding to using the spectral decompositions. So, keep it in mind this, and we have to take a matrix is symmetric, and then we can generate like that. So, any symmetric matrix can be reconstructed using its eigenvalues and eigenvectors. For example, for a spectral theorem decomposition, let A be a symmetric matrix and positive definite. Symmetric matrix mean you take a main diagonal, above diagonal and below diagonal are same, right. So, here minus 4, 0.4 and 0.4 are reflected in first row second column and second row first column. Therefore, even if you take A and A transpose, so A equal to 2.2, 0.4 and 0.4 and 2.8, and then A transpose equal to change rows to the column and columns to the rows, and then here 2.2, 0.4, 0.4, 2.8 will come, and A transpose are equal, then it is said to be a symmetric matrix. Now, let us start. Determinant of A minus lambda I equal to 0, find out. Now, you know the technique of finding the determinant, right. So, after substituting A matrix and lambda into identity matrix, and the resultant will be lambda square minus 5 lambda into 6.16 minus 0.16, and simplify, and we have lambda minus 3 into lambda minus 2 equal to 0, and we have two values of lambda, one is 3, another is 2, that is called it as eigenvalue. Now, based on this eigenvalue, we have eigenvectors corresponding to eigenvalues, that is E1 lambda transpose is 1 by root 5 and 2 by root 5, E2 transpose is 2 by 5 minus 1 by root 5. So, this is the corresponding eigenvector. Consequently, we can split it into 3 values of A equal to 2.2, 0.4, 0.4, 2.8 can be written as. Now, we have 2 values according to previous theorem. Previous theorem says that you know the lambda 1, lambda 2 and so on lambda k, and then eigenvalue E1 and E1 transpose. Here E1 transpose, you know E1 is like that, then E is 1 by root 5 and 2 by root 5 into E2 transpose, E1 transpose you have to write it, and then here 2 rows and 1 column, here 1 row and 2 column, the resultant is 2 rows and 2 columns will come into multiply with 3, so that the answer is 0.6, 1.2, 1.2, 2.4 will come. Similarly, plus lambda 2 is 2, and then the E2 is 2 by root 5 minus 1 by root 5 into E2 transpose is 2 by root 5 minus 1 by root 5, and this is a 2 cross 1 matrix. This is 1 row and 2 column. We have 2 rows and 2 columns. Multiply with 2, we have 1.6 minus 0.5 minus 0.8 and 0.4, and simply add them. That is the meaning of A, and A can be expressed like that. This is the corresponding spectral decomposition of the given eigenvalue and eigenvector. Now, eigen decomposition is not a unique, because decomposition is not a unique when 2 eigenvalues are the same. By convention, order entries of tau is a descending order, then eigen decomposition is unique if all the eigenvalues are unique. If any eigenvalue is 0, then the matrix is said to be singular. Singular means determinant equal to 0. Now, for positive definite matrix, a matrix whose eigenvalues are all positive is called a positive definite. If eigenvalues are positive or zeros, then the matrix is called as positive semi-definite. Positive definite matrix guarantee that x transpose Ax is positive for any non-zero vector x. Similarly, positive semi-definite guarantee that x transpose Ax is always positive. And singular value decomposition based on the definition 1, write A as a product of 3 matrices A equal to UD V transpose, and A is a M cross N matrix, U is a M cross M matrix, and D is a M cross N matrix, and V is a N cross N matrix. So, check U and V are orthogonal matrix and D is a diagonal matrix, it is not necessarily square. So, diagonal entries of D are singular values of A, and columns of U are left singular vectors and columns of V are right singular vectors. Next, based on the definition 2, SVD can be interpreted in terms of the eigen decomposition. Left singular vectors of A are the eigenvectors of A transpose. Right singular vectors of A are the eigenvectors of A transpose A. So, non-zero singular values of A are square root of eigenvalues of A transpose A and A transpose. Next, the deep into eigenvalue decomposition. How determining the eigenvalues and eigenvectors of the matrix 2 by 2 in the case is pretty much all the work of what's eigenvalue decomposition. So, we will start with this matrix representation as a linear transformation 0, 1, minus 2, 3 according to the picture. So, you can see the action of the matrix at the right. It sends 1, 0 vector to the 0, minus 2 and 0, 1 vector to the 1, minus 3. So, that is a representation of the matrix from the picture. Now, the eigenvector of this transformation are any non-zero vector that do not change the direction during the transformation, but only clap up or down by a factor of lambda as a result of this transformation, right, 0, 1, minus 2, minus 3 of R1 R2 equal to lambda of R1 R2. So, this way we can represent the vectors corresponding to the matrices. Now, using our calculation of the previous post, we calculate the lambda and lambda, that is lambda 1, lambda 2 are the two factors will comes corresponding to more generalized of the eigenvectors, let it be R minus 2R minus R respectively. So, R may be any real number and then we can expand into the what these ideas. Now, in the corresponding picture, the red vector represented minus R to R, right, and then the right starts at minus 1, 1 and scaled by the eigenvalues of minus lambda during the transformation, the meaning it simply turned the opposite direction and its magnitude does not change. So, that is the pictorial representation to corresponding to the vector. So, any vector of the form minus R will behave the way during this transformation, that is the inference. Next, the purple vector representing the eigen vector of R comma minus 2R and then it starts from minus 1 comma 2, it is scaled by the eigenvalues of minus 2 during the transformation, it turns in the opposite direction and scale the factor. So, the factor of the form R comma minus 2R will behave the way during the transformation. So, this can be decomposed. Now, we can now use the equation of the above and plug in each eigenvalues and corresponding eigenvector. So, to create the two matrices of vector corresponding, multiply them to the given matrix, you have 2 times of minus 1, 2 will come, another one is minus 1 times of minus 1, 1 will come. So, that is the expand from the domain to the codomain and we combine the items of the left side of the each equation and the items on the right side of the equation, we can write the decompose as 0, minus 2, 1, 3 and 1 minus 3 corresponding the vector minus 1, 1 and 1, then we have minus 1, 1, 2, 1 and 2 minus 2, 0, 0 minus 1 can be decomposed. So, the original matrix is 0, 1, minus 2, minus 3 can be eigenvectors, you have to write the matrix, eigenvalue write the matrix, then inverse of the eigenvalue, that is the meaning of decomposition. So, and combine the transformation representation of the matrix, we have the original matrix. So, that is the picture representation corresponding to the matrices. So, now we have an example. Let A be a symmetric and positive definite matrix, and U can be computed as what? It is not a square matrix, and compute the square matrix A transpose, which is equal to, so this is 2 rows and 3 column, A transpose is 3 rows and 2 column, so that the answer is 2 cross 2. Now, it is easily find the determinant of what eigenvalue eigenvector. Therefore, determinant of A transpose minus I equal to 0, that is lambda I equal to 0. Then nu 1 is call it as lambda 1, nu 2 is called it as lambda 2. We have 2 eigenvalues and corresponding to eigenvectors of 1 by root 2, 1 by root 2 in orthonormal. Therefore, 1 by root 2 minus 1 by root 2 another eigenvectors corresponding to 10 and 12 respectively. Now, V can be computed as, the rule is A you know, A transpose A you know, and then multiply them, so that you have a what a matrix, because this can be written as previously written A transpose, now we written as A transpose A. So, A transpose A put 3 cross 3, A transpose we have a what 2 cross 2. Now, based on this we have a eigenvalue eigenvector. So, once you get it A transpose A, then the determinant of A transpose A minus lambda I equal to 0. We have lambda 1, lambda 2, lambda 3 or the 3 eigenvectors generated. Based on this eigenvectors corresponding to this we can do. So, that is the inference we have learned from the what if it is matrix is symmetric like that. So, you see the answer of this is symmetry and this is also symmetry, that is the inference. So, based on this we have to take lambda 1 square equal to 12, lambda 2 square equal to 10, and the singular value decomposition of A equal to what? The lambda 1 into the eigenvector corresponding to this and this into this multiply, so that U, V and tau are computed by performing the eigen decomposition A transpose and A transpose A. So, any matrix has a singular value decomposition, but only the symmetric and a positive definite matrix have an eigen decomposition. So, that is the inference. Now, we have application of SVD in linear algebra. So, inverse of n cross n square matrix A. If A is a non-singular, then A inverse is UA U V transpose whole inverse is V A transpose U transpose, where tau transpose is a diagonal of inverse of lambda 1 by lambda 1, 1 by lambda 2 and then 1 by lambda n. And if A is a singular, then A inverse equal to U tau U V transpose minus 1, which is equal to what? V A tau naught transpose U tau, where tau naught transpose is a diagonal of 1 by lambda 1, 1 by lambda 2 and so on this. So, for the least square solution of m cross n system, convert given matrix to the square matrix and then Ax equal to B. The technique is A transpose Ax you have to find out, and then it become A transpose B will come and check it out, x equal to A transpose A the whole inverse, and then we have A transpose B equal to A plus of B. So, A plus B means A transpose. So, A transpose A is a singular, then A plus B by B of 1 by 4 of V tau naught inverse of U tau naught B can be calculated. So, the lambda tau naught square is a diagonal of inverse of the eigenvalues. So, that is the what condition we learned from this type of the matrices. So, condition of the matrix is measures the degrees of singularity of A, and larger value of lambda 1 by lambda n, closure A is being a singular. Now, in a linear further application is we have a homogeneous equation Ax equal to 0, and then minimum norm solution is x equal to 0 is a trivial solution, and impose a constraint norm x equal to 1, and we apply the optimization problem of minimum of norm of x, you have to find out. That will be discussed in the next topic. And a special case, if rank of A equal to n minus 1, where m comma n minus 1 lambda n equal to 0, then x equal to k v n, where k is a constant. In general case, find the rank of A and should be n minus k, and m comma n minus k and lambda suffix n comma n minus k plus 1 is tau, which is equal to lambda n equal to 0, then x equal to k1 Vn minus k plus 1 plus tau plus kk Vn, where k1 square plus tau plus kn square equal to 1. So, if you want to prove, and then we have to demonstrate like that, and as appeared before, homogeneous solution of the linear system of equation, computation of homography of using DLT, and estimation of fundamental matrices. Now, what is the use of SVD? SVD can be used to compute optimal low rank approximation of arbitrary matrices, and it may analyze face recognitions, represent the face image as the eigenfaces, and compute distance between the query face image in the principal component space, and applying the data mining, the latent semantic index for document extraction, and image compression, write a Carnon-Liouville transform, perform the best image compression, like MPEC discrete cosine transform has the closest approximation in KL transform of PS and R. So, the beauty of this, that it is only of theoretical importance, and there is no way it can be of any practical use whatsoever. So, this is the illustration. If you are non-square matrix converted into square matrix and decomposed into the matrix like this, and even if it is inverse is a non-square matrix also, we can do the decompose using the ideas. So, that is the application of SVD. You take a m equal to 3 rows and n equal to 2 column, then we can have the SVD split into decompose like this, and you do it yourself of finding these values, and then the approximation is low rank. SVD can be used to compute a low rank approximation, and we have a rank of AK using the optimal ideas like a Frobenius norm, and norm of F is a distance of this. AK and X are both m cross n matrix, typically want K is less than, very less than R. So, the solution is through singular value decomposition, and AK can be expressed U into diagonalization of matrices and the decompose into this, and AK can be written as summation I equal to 1 to k sigma I ui vi transpose. So, the column rotation is a sum of the rank of the matrices. Now, we have approximation. How good or bad is the approximation? It is the best possible measured by the Frobenius norm of the error, like using the technique of norm of A minus x, minimum of this one, you check it out, and we have a norm of A minus AK is equal to sigma of k plus 1. So, where sigma are the ordered such that sigma is greater than or equal to sigma I plus 1, this suggests the Frobenius order drops as k is increased. Now, we have application. So, matrix decomposition as an important concept in linear algebra. It allows us to represent the matrices with respect to different bases and decompose into meaningful part. As stated at the beginning, the decomposition encompasses the classical approaches to statistical data analysis, such as number 1, principal component analysis, number 2, Fisher discriminant analysis, number 3, multi-dimensional scaling. So, it will dig into what principal component analysis in the future post. However, it is important to note that Eigen decomposition is used only for square matrices. So, the more general method of matrix decomposition that can be applied to non-square matrices is the singular value decomposition, which will be discussed in the next ideas, where I will also use the SVD for image compression and shows some of its applications.